Hi, I'm Jenny, and I'll be talking about the misuse, misreporting, and misinterpretation of statistical methods in usable privacy and security papers. This work was done with my wonderful advisors, Lujo, Bauer, Nicolas, Christin. So let's start with a pop quiz. Please raise your hand if you've seen or written something similar in a paper, that because a p-value is at or below a certain threshold, a result is significant. All right, keep your hands up if you are very confident that you did this completely correctly from the process of getting that value, reporting all the info, and interpreting what it means. Not sure I see any hands. Well, we find p-values useful and see them a lot because statistical significance testing is often used as support for scientific results. We get some data, and we put it into a statistical test, such as a Fisher's exact test, paired t-test, regression, or whatever else, and we get a p-value and sometimes an effect size, or we calculate that ourselves. We interpret these outputs to discuss whether or not some effect exists, often based on whether it meets a p-value threshold. We also ideally interpret the impact of that effect and what it might mean in practical terms. From these, we use these to make a claim or assertion about the world. For example, maybe that users understand warnings with triangles better than warnings with rectangles. Now, these can lead to proposed interventions, policies, and designs that help protect user privacy and security. And these claims are often supported by p-values, which we kind of see as objective measures of truth about what is being investigated. But statistical significance is not sufficient in and of itself. Sometimes some things go wrong in this, whether in the process of getting that p-value, reporting it, or interpreting it. So we wanted to know how often we get some aspect of statistical methods wrong in practice in published papers. And I know it's still a little abstract, so before I tell you how we study that and what we found, let's read a SOUP paper as an example to introduce some of the things that could go wrong with how we use, report on, and interpret statistics. And when I say SOUP paper, I mean a paper about soup. And the premise is this. A restaurant wants to know whether to sell miso soup or clam chowder, using statistical tests to investigate this. And this SOUP paper collects data from 100 users, half of whom get miso soup and the other half get clam chowder. It asks how much people are willing to pay and their opinions on the soup they get. Well, what could go wrong? Well, sometimes the statistical test doesn't match the data, which we call statistical validity issues or misuse. One example is when the test is incorrect. We might see this line in our SOUP paper, that we run a paired t-test on the amount of money users would be willing to spend on clam chowder compared to miso soup. But the paired t-test is not suited for the data because users are randomized to one of two conditions, so it should be a test for independent samples, such as a two-sample t-test. I want to quickly note this is not meant to be a tutorial about what the right test is in each circumstance, but just an example of an incorrect test. Now, given that misuse of the test for the data, the resulting p-value and statement of whether an effect exists based on that p-value is not valid. We might also see reporting issues or misreporting in our SOUP paper. And one example is when reporting is lacking so that the impact of the effect cannot be properly determined. Assuming that we ran the correct two-sample test in the previous example, this could be the result, that users would spend more money on a bowl of clam chowder than on a bowl of miso soup, supported by a p-value. However, this doesn't tell us how much more people are willing to spend, right? Or the magnitude of that difference. Is it 1 cent more, or is it $9 more? Those mean very different things, and the lack of reporting or misreporting leads to difficulties of evaluating the impact of that result in context. Finally, there might be interpretation issues or misinterpretations, where the result from the test is interpreted in a way that is incorrect or misleading, such as interpreting p-values as effect sizes. We might see this statement in our SOUP paper. Users like clam chowder much more than miso soup with a small p-value. But without further context, rather than interpreting the small p-value as the high likelihood of the existence of an effect, it's interpreted as a large effect size, which is not what actually the result supports. So now we've seen examples of issues that might occur in a SOUP paper. What about their occurrence in SOUPS papers? Well, we conducted a systematic review of 121 SOUPS papers that use statistical significance testing. These were drawn from all papers at SOUPS published in even-numbered years from the start of the conference, so that's 223 papers, and which had at least one statistical test, narrowing it down to 121 papers over 10 years. We read all 121 papers carefully and identified and coded every instance of a statistical test. More details are in the paper, but I'll give a brief overview of our methods here. We developed the codes for possible issues by first reading through a subset of papers in 2 years to identify things that may be wrong. We also supplemented those with APA reporting guidelines, which are often seen as a gold standard for quantitative methods reporting, so as a source of how to report and interpret things correctly. This led to our initial codebook. We then further went through these issues and iteratively grouped them to the broad categories of misuse, misreporting, and misinterpretation, and associated subcategories. After these codes were complete, we then applied them and coded all 121 SOUPS papers like we did with our SOUP example. A subsample was also double-coded. So, how did we as a community score? Well, misuses occur in 65% of papers. And there are 3 subcategories of these, and I want to highlight 2. I want to also quickly note that papers can use more than one statistical test, so there can be more than one issue present in the same paper. Now, incorrect tests appear in 23% of papers. And these occur when tests do not properly account for dependencies between the data, such as in our example that uses a paired test rather than one for independent samples to compare clam chowder and miso. Tests are unverifiable, or at least one test is unverifiable in 51% of papers. And this occurs when there is insufficient information about a statistical test or the associated variables. For example, if we see the statement that a statistical test shows higher user ratings of clam chowder compared to miso soup, but it never tells us which statistical test they ran. So readers are unable to verify if the statistical test is actually suited for the data. Misreportings occur in 95% of papers, so almost all papers. There are 3 subcategories and 2 I want to talk about specifically. The first is scientific significance issues occurring in 80% of papers. And this captures when there's not enough reporting to show the potential impact of an effect, even if the ultimate conclusion that an effect exists likely holds. So we can see this in our example that people would spend more money on clam chowder without reporting on the magnitude of that difference. The other type I want to mention is statistical significance issues, which occur in 86% of papers. This occurs when best reporting practice is not followed for the statistical result. For example, this reporting of the results from a chi-square test of independence, which gives us test statistics, but not degrees of freedom or exact p-value. Finally, misinterpretations occur in 45% of papers. And once again, 3 subcategories, 2 I want to talk about. Improper interpretations crop up in 27% of papers, where the result is interpreted in such a way that does not match the assertion, such as conflating statistical significance and effect size, as seen on our example on how users prefer clam chowder. Another subcategory of no interpretation, appearing in 7% of papers, occur when tests are conducted, but not further addressed or explained in the table, or paper, such as just leaving a regression table in the paper with no further comments. Now, we didn't just want to know about how often issues occurred, but also want to know the impact of these issues on the ultimate assertions made by a paper. So we analyzed this, and I want to point out a few findings. Some issues affect the impact of the assertion. And so from our SOUP example, an assertion could be that because tests found that users would spend more money on clam chowder than miso soup, we would make a lot more money selling clam chowder. However, because we don't actually know how much more money users would be willing to pay, it could be just a few cents, and it costs a few dollars more to make clam chowder. So the final assertion that we would make more money is not completely supported. So these types of partially supported assertions, where information to judge effect size or direction is not fully present, affect assertions in 44% of papers. Other issues affect the validity of the assertion. So in our SOUP paper, because a paired t-test found a difference between how much money people would be willing to spend on clam chowder and miso soup, we might say that we should sell clam chowder and not miso soup. But this assertion is based on a test that isn't suited to investigate what we want to. And thus, we don't know whether that assertion is valid, because the results from the chosen test cannot support it either way, due to it not being the correct test. And assertions in 47% of papers are not supported in this way. Finally, some issues affect the evaluation of the assertion. If in the SOUP paper we have this comment that a statistical test finds that higher ratings of clam chowder occur, well, we could assert that we will make more money selling clam chowder than miso soup because it's more popular. But there's not enough information to determine if that claimed effect exists, because we're lacking information to determine whether the chosen test is actually the correct test. And this lack of information affects assertions in 58% of papers. And given these issues, we put forth recommendations for authors, reviewers, and readers who use statistical testing in their work. We don't have time to read it. Recommendations are discussed further in the paper itself, but this checklist highlights things that can help ensure enough information is reported to reconstruct the test and evaluate its appropriateness, which affects 58% of papers, or to provide further context for the assertions, which were not fully sufficient for tests in 44% of papers. So, overall, issues are common in the usable privacy and security papers we analyzed, with some impacting the evaluation results, while others impact their validity. Misuse occurs in 65% of papers, misreporting in 95%, and misinterpretations in 45%. Of course, the paper itself has more nuance and details on all of these, and I encourage looking at that. I want to conclude with the reflection that statistical significance may be expressed through a statement like p less than or equal to 0.05 is often a step towards supporting an assertion, but is almost never sufficient in and of itself. Beyond the fact that sometimes there are mistakes in choosing the right statistical test, how that test is reported and interpreted is critical for understanding the significance of our findings, not only in statistical terms, but also in terms of scientific context and practical impact for users, authors, and our research community. Thank you very much, and you can find the paper here.